అన్మ్యూట్ అయితే స్ట్రీమ్ ఇచ్చేస్తున్నాను. ఇందులో స్టార్ట్ వస్తున్నట్టు రీసెంట్ రీసెంట్ స్టార్ట్ చెప్పండి.
Hello? I'll start in I'll start here. Okay. That's it.
Good morning, all of you. Before actually going into the GATE coaching, which is actually being started by the government of Andhra Pradesh for the sake of the students of entire Andhra Pradesh, let me introduce myself to you. This is Professor K. Govinda Rajulu, Principal and Professor of Mechanical Engineering, Jawaharlal Nehru Technological University, Anantapur. Actually, I started my career as a lecturer in the year 1985, got promoted as associate professor in 94, and further as professor in the year 2000. From 2000 onwards, I have served the university in different administrative capacities also, and I worked as the controller of examinations of the combined JNT University for more than 4.5 years, and director of evaluation for 1.5 years, and further as for UGC Academic Staff College, and simultaneously I worked as the convener for statewide entrance examination ESET as a convener for 3 consecutive years of 2005, 2006 and 2007. Apart from this, I worked as a Director Foreign Affairs and Alumni Matters after coming back to JNTU Anantapur, and I worked as the Director of Evaluation, and I worked as the Principal for JNTU EA College of Engineering, Govinda for more than 4 years, and I worked as the Officer on Special Duty more than a year, and at present I am the Principal, JNTU EA College of Engineering, Anantapur, and I'm very glad to inform you that I'm a recipient of the Best Teacher Award by the government of Andhra Pradesh, and I contributed in all the posts that I had done to the university, and I doesn't want to list all the achievements that I have made and all, and total I have 35 years, more than 35 years of teaching experience and all, published many international, national journal papers, and published papers in the national and international conferences, and organized many conferences and workshops as principal, as a professor of mechanical engineering and all. With this brief introduction, let me start the coaching for the GATE, which the JNT University has taken up on behalf of the government of Andhra Pradesh. So, as a part of this, I'll be taking up a subject called as the refrigeration and air conditioning. Probably all of you might have studied as you are preparing for the GATE. Definitely, you might have studied the subject of refrigeration and air conditioning. So all of you know, so in order to go for air conditioning, first you should know what is refrigeration. Just before going into the subject of refrigeration in the gate point of view, I would like to refresh your memory regarding the fundamentals of the refrigeration. What exactly you mean by the refrigeration? The general point of view, if you ask a layman, then definitely will reply to you that refrigeration, what is there? It's the temperature which is lower than the surroundings. This is, in general, we reply like that, isn't it? Anybody who knows about the refrigeration, because it's a common word, everybody might have heard about the refrigeration. If the temperature is lower than the surroundings, then we call this as the refrigeration. That's correct also. But in the point of the refrigeration engineering, then as a definition, if you want to say what is the refrigeration, it is the artificial removal of heat from a substance or a space. What for? To produce a temperature. How much? Lower than that of which would have existed. This is how you define the refrigeration. Therefore, it is the artificial removal of heat from a substance or a space to produce a temperature lower than that which would exist. This is how we define theoretically the refrigeration. Before going further, definitely we should know how to measure refrigeration. How do you measure it? What are the units for it? How much quantity of the refrigeration has been taken up? Definitely, then the famous unit for refrigeration is the standard unit. It's called as 1 ton of refrigeration. Usually, it is denoted by 1 TR, capital T, capital R. T stands for ton, R stands for refrigeration. Definitely, if one has not heard about the 1 ton of refrigeration, then definitely will get amused. What is this tons? Tons is something like a weight, 1000 kgs and all. But here, this unit is being framed in such a way that this 1 ton of refrigeration is equivalent to the rate of heat transfer needed to produce. What is that you have to produce? 1 ton of ice. This is how it has come. 1 ton of ice. At what temperature you need to have the ice? At 0 degrees centigrade. From where? From water. Water at what temperature? Water at 0 degrees centigrade. In how much amount of time? In 24 hours. 24 hours of time. So comprehensively, to define a unit for refrigeration, this is a unit of refrigeration. It is equivalent to the rate of heat transfer needed to produce 1 ton of ice at 0 degrees centigrade from water at 0 degrees centigrade in 24 hours of time. In one day, we have to produce 1 ton of ice from water at 0 degrees centigrade to ice at 0 degrees centigrade. This is how we define. That means how much of heat energy it comes to, how much of heat energy it is to be removed. That means, say the temperature is same, water at 0 degrees centigrade is to be converted to ice at 0 degrees centigrade. What does it mean? That means we have to take out the latent heat of fusion of ice. How much it is? It is 335 kilojoules per kg. Then, like that, not for 1 kg, for 1 ton, the amount of heat to be removed is 335 kilojoules. Then for 1 ton, it is 1000 into 335 kilojoules. In what time? In 24 hours of time. So usually we take in terms of time, in terms of minutes or seconds. So in terms of minutes, if you take, then it is 1000 into 335 divided by 24 hours into 60, that will give you the kilojoules per minute. Then quickly, if somebody calculates with the help of a calculator, then definitely he will point out to me that, sir, here you have written this as 210 kilojoules per minute, but I have calculated, see, the number that I am going to get is not 210. Then definitely if you calculate, you might have got this value as 232.6 kilojoules per minute. Further, in terms of kilojoules per second is a kilowatt. Per second, if you convert this into second, that means you divide this with further 60. 210 divided by 60, it comes to 3.5. What is this kilojoules per second? Joules per second is what? Kilowatt. It is 3.5 kilowatt. So people have simplified this. Then if you convert this instead of 210, the 232.6 divided by 6, you will be getting more than this 3.52, something like that you will be getting. But the simplifications will become a difficult thing. So in actual practice, the refrigeration and air conditioning engineers have accepted that 1 ton of refrigeration is equal to 3.5 kilowatts. But it is not strictly according to the definition that we have given. Once again, let me repeat that. If you, according to the definition, if you take up what is the latent heat of fusion, 335 kilojoules per kg multiplied with 1000 kg divided by 24 hours into 60, then this value you are going to get as 232, and this will be more than that. So what is that we have done? We have simplified this, and it has been accepted by all the refrigeration and air conditioning engineers that 3.5 kilowatt is 1 ton of refrigeration, and in terms of the kilojoules per minute, it is 1 ton of refrigeration is equal to 210 kilojoules per minute. So you should know the definition actually as what is being practiced by the refrigeration and air conditioning engineers. Then you should remember always that 1 ton of refrigeration is equal to 3.5 kilowatt as well as 210 kilojoules per minute. Is very, very important. Throughout this topic, refrigeration as well as in the air conditioning, very, very frequently we will be making use of 1 ton of refrigeration and its value. Therefore, always you should remember this value. Okay? With this background, let us go a step further. This is 1 ton of refrigeration. It's good. And what is refrigerating effect? What do you mean by refrigerating effect? What is this effect? That is nothing but effect means you are producing some amount of the cooling. Then what is the amount of cooling that you are producing or a system is producing? There's nothing but refrigerating effect. In raw terms, it is nothing but the amount of cooling that is being produced. That's a very simple thing. What is this? Refrigerating effect is nothing but the amount of cooling produced by a system. Then what is the amount of cooling produced, or it is also defined as it is the amount of heat removed in terms of the kilojoules from the application by a refrigerant. By a refrigerant, then what is the amount of heat removed from certain application? This is called as the refrigerating effect. Now, refrigerating effect and seen units of refrigeration. With this, let us go a step further. Usually, whenever the engineers are involved in some of the things, definitely we will go for the things. What is the performance? How it performs? Always engineers will be thinking, how do we define the performance of it? Always will be thinking how to improve the performance of it. It is a continuous process. Every time the engineers will be thinking how to improve the performance of one particular thing. This is usually happens, and continuously engineers are in a position to develop much better systems with better efficiency. So, in order to know that, better efficiency means efficiency is the parameter to know the performance. Usually in terms of heat engines and other things, the performance of a heat engine is rated in terms of its efficiency. Here, the performance of a refrigerator is not in terms of its efficiency, but a different term that is called as the coefficient of performance. So, if that is the case, then how to define this coefficient of performance? Now, let us go a step further. How it is defined? Refrigeration is nothing but extracting the heat, isn't it? Then it is defined as the coefficient of performance is defined as in the refrigerator, that is also called as refrigerating effect that we have seen earlier. 2. The work done on the refrigerant to achieve that refrigerating effect. How do you achieve this refrigerating effect? The work is to be done on the refrigerant. That is the input to you. This is the input to you. And the output is the heat is being extracted. Usually the efficiency or performance, then what is the output that you are getting divided by the input that you are giving. Usually in the case of the heat engine, because mechanical engineers are very much conversant with the heat engines, IC engines or whatever engines it is, the efficiency, how do you define this? Efficiency is equal to work output. For this we are giving the heat input. Therefore, work output by heat input. Usually we define that way the efficiency for a heat engine. But here this is defined as the heat extracted, because what is that we require in the refrigerator? In the refrigerator, we require the heat is to be extracted. Therefore, that we call this as the refrigerating effect. That is the output that we want. Heat is to be extracted. That is Q. So, to extract that, what is the rate? Therefore, output by the input. Once again, this is the COP. COP for the refrigerator is defined as Q by W. Q by W. Remember once again, what is Q? Amount of heat extracted. So in the refrigerator, the output that you are getting is the amount of heat extracted. And what is W? Work input. In order to extract the heat, you are giving work input, or work is to be done on the refrigerant, that is output. So general definition of any performance parameter, it may be an efficiency or it may be coefficient of performance, it is nothing but the output that you are getting by the input that you are giving. Therefore, it's very simple. Q and the input you are giving is W. Therefore, if you know the general definition of the performance, nothing but output by input, this is what it is given. But if you remember the definition for efficiency, there is also performance parameter for a heat engine, that is nothing but their output is work, input is heat, therefore that was W by Q, heat. What does it mean? It is exactly the reciprocal of the efficiency of a heat engine, reciprocal. And therefore, the reciprocal means in the case of the heat engine, all of us know the efficiency will be always less than 1 and it will be a fraction less than 1. And it is a reciprocal of it, therefore, it will be definitely greater than 1. Therefore, what is the COP? That is always greater than 1. Why? Because it is the reciprocal of efficiency of a heat engine. Reciprocal means 1 by the efficiency. Efficiency is always less than 1. Therefore, 1 by fraction will always be. Therefore, all of you should remember that the COP of a refrigerator will be always greater than 1. It is a really objective type of question, even in the university examinations or in the interviews and all. Usually, you'll be asked to explain the COP and its value and you will be asked to know why it is greater than 1. The explanation is very simple. If you remember this, then definitely we can say that the reciprocal of a fraction will be definitely more than 1, and that's how the COP of the refrigerator will be always more than 1. Okay, now let us go. Yes. What is relative COP? What is relative means you are comparing with something different, isn't it? Actually, all of us know, theoretically speaking, the performance, it may be COP or efficiency, it will be highest. And practically, there will be many difficulties involved in it. Practicality will be involved in it. Because of it, you will not be in a position to achieve the theoretical COP, but you will be getting something less than that. And always engineers will try to achieve the theoretical COP, which is the highest thing that we can achieve, isn't it? Therefore, we should know the relative COP, where we are get the theoretical COP. In order to know that, you should know the relative COP. If you say that the relative COP is 50%, immediately engineers will jump and say that there is a lot of scope for the engineers to improve the COP, because it is not as per the theoretical one. Therefore, lot of practicalities are involved. Because of this, the COP has gone down. Then how to improvise the process involved in the cycle? Always we'll be thinking about that, and definitely we'll be looking for improvement in the processes. Therefore, it is really important to know what is a relative COP. What is a relative COP? How it is defined? It is defined as the actual COP of a refrigerator to the theoretical COP of that particular cycle. Always the theoretical cycle, the COP will be definitely more than the actual COP. It will be definitely less than 1, and therefore this is how you can calculate the relative COP, and it is always important for an engineer to know what is the relative COP of it. Okay. Now with this background, let us, so before actually going into the refrigerator, then let us understand, because all of us are very much familiar with a heat engine. And if you see, one diagram has been shown here. It's really very interesting. There is engine, whatever it is, you take one system is there, and there is a hot body, there is a cold body, and there is input is given. This you see, from the hot body, some heat input is given to the system. It's coming inside the system, heat input. This is Q in. It is QH or Q in, whatever you call. That means heat extracted from the hot body. From the hot body, we are extracting the heat that is coming into the system. Okay? And we know that. And the heat coming into the system, a part of it is being rejected, isn't it? With the flue gases, exhaust gases, and all in the heat engine, we will be rejecting some amount of the heat. It's a basic understanding all of us know. So the system taking some heat from the hot body, and by rejecting some heat to the cold body, it is in a position to develop some amount of the work. Some amount of the work. How much amount of the work? Therefore, the heat it is being taken in is Q in, and it is given out is Q out. Where the remaining amount of heat has gone, it has been turned up into the work of the cycle. Therefore, the work done by the cycle here is nothing but the amount of the heat taken in minus amount of heat given out. This is nothing but Q in, or usually we will write this Q in as QH. It is nothing but the heat taken from a hot body, and Q out is QC, heat given out to a cold body. This is QH minus QC, or Qn minus Q out is being converted as the work done per the cycle. this amount of the work done. This is equal to heat taken from this and given out to this. This minus this is nothing but the work done. It's very simple, because as we know the heat engine, it becomes easier for us to understand a refrigerator. A refrigerator or a heat pump. Refrigerator or heat pump, this system diagram is going to be the same. Now, let me explain how it is. How, if you see this figure, it is just similar to the heat engine. Now, let us see here, but earlier the heat was taken from the hot body. If you see here, the heat is taken from the cold body. This is the refrigerator. Heat is taken from the cold body, that's why it is getting colder, isn't it? That means the heat is taken from the cold body, and on this system, some amount of the work has been done, some has been done onto it, and some amount of heat is rejected to the cold body. In order to reject it, some work is to be done onto it. Otherwise, on its own, it cannot reject the heat from a cold body to a hot body. It is not possible. Some work is to be done onto the system in order to make the heat to be rejected from cold body to the hot body. Then, what is the amount of the heat that is being rejected to the hot body? Interesting, isn't it? Definitely would like to know what is the amount of heat rejected to it. That is, whatever heat it has been taken away from the cold body, this is Q in, and whatever is the amount of the work done on the system, both combinedly, this will be converted into the work is converted into the heat, and the total amount of the heat will be rejected to the hot body. Therefore, what is this work? This heat taken in, Q in plus W is equal to Q out. It is QH, isn't it? That means what is W? The W is nothing but this is Q out minus Q in. Q out minus Q in. It is reverse here. It is reverse. Okay, Q out and Q in. Got the point? I hope all of you might have understood this. Some amount of heat is extracted from a cold body. That's why it's called as a refrigerator. And in order to reject the heat to a higher temperature body, some work is being done. Therefore, total amount of the heat rejected is heat extracted, that is QC plus W is equal to QH. Therefore, what is the work done per cycle? Work done per cycle is equal to, this is Q out, this QH, and Q minus Q in, it is QC. Same. Therefore, work done per cycle is equal to Q out minus QC. Therefore, and what is a refrigerator and what is a heat pump? Refrigerator, the basic purpose is to extract heat from a cold body. So, we are interested to know what is the amount of the heat extracted from the cold body. That's why we call it as a refrigerator. But the cycle, I told you in the beginning, that this is the cycle for heat refrigeration as well as for a heat pump. Now, how it is also a heat pump? What is requirement in the heat pump? That you should understand. What is required here? Required is some heat is to be delivered to a hot body. That is requirement. Here in the refrigerator, heat is to be extracted from a cold body. This is our requirement. In the case of a heat pump, the requirement is heat is to be supplied to a hot body. How do you supply the heat to a hot body? Once again, the same thing. Removing from a colder body by giving work input to it, both combined together, it will be given to this. That means what is required, what is output required here and what is output required here are different. But the same machine will work as a refrigerator on one end and as a heat pump on the other end. Then how? Then what is required in the refrigerator? In the refrigerator, what we require is the heat to be extracted from a cold body. That is the output that we require. Output, what is the output that we require here? The amount of heat to be extracted from a cold body. And what is input given here is a work. Okay? For a refrigerator, then The output is the amount of heat extracted. This is QC or QN. And the input given to is W, work done, isn't it? Now, in the case of a heat pump, what is that you are looking for? What is required for you? Heat is to be rejected. Heat is to be supplied to a hot body. Therefore, what is the amount of heat given to the hot body is the output that we require. So, what is the difference here? The output is difference. If you take this as a refrigerator, the output is heat extracted in the cold body. And if you consider this as a heat pump, the output of this is heat given out to a hot body. Heat supplied to a hot body. Therefore, output is different. Output is different. And for both of them, what is the input? It's the work. Even for the to extract heat from the cold body, input is W. To supply the heat to the hot body, we have to supply a W. So this supply, this is always same, but here the output in the case of a refrigeration and a heat pump are different. If you can understand this concept, then it becomes very easier for us to know the relationship between the COP of a heat engine and a refrigerator and a heat pump. It's very easy. With the help of these two figures, we can always remember what is the COP for these three things. So before going to that, we should know the temperatures where they operate. This is very much important to know. The heat engine, a refrigerator, and a heat pump. Okay? Heat pump, then how, in which temperature ranges these things will work. This is very important thing. If you can understand, then understanding the remaining things will become easier for you. Now, what is this dotted line? If you see this, this is TA. This is called as the atmospheric temperature. Atmospheric temperature. Therefore, first let us take up with the heat engine. This is the heat engine. In the heat engine, there is a heat source, and this is at temperature or above the atmospheric temperature. Very high temperature heat source is available to you in the case of a heat engine. Therefore, in the heat engine, heat is drawn at high temperature from this heat source, and once again slightly above the atmospheric temperature. Slightly above the atmospheric temperature. This T2 is slightly above, greater than or equal to atmospheric temperature. Greater than or equal to atmospheric temperature. And the remaining amount of the heat is being converted as the work. This is how the heat engine operates. Now, similarly, let us take up from a refrigerator. Refrigerator, if you see, this is atmospheric temperature. This is at lower temperature than the atmospheric temperature, and it is extracting the heat from a temperature. This is less than the atmospheric temperature. EO is less than the atmospheric temperature. From that, it is taking out the heat. It is further cooling and maintaining this less than the atmospheric temperature. And always it will be continuous to extract the heat from a body which is at a temperature lower than the atmospheric temperature. It continuously taking up the heat from this. Therefore, and there is a, see here, there is a pump here, there is a compressor, whatever it is, engine, or here the work is being supplied. Why work is being supplied? Whatever you extract the heat is to be rejected to a heat space or hot space. In order to extract to a space where the temperature is more than this, some work is to be done on the engine. Some work is to be done, and this is the heat pump and the refrigerator. Both the cases, this heat will be rejected. It will be taken from lower space and it is rejected to the heated space. This is how H means it is a heat pump, this is the heat engine or is a refrigerator or is a refrigerator. Okay? Now, if you see this, now the temperature, how much heat is being supplied to the heated space is important. This is the TK. This is much above the atmospheric temperature, much above the atmospheric temperature, and heat is extracted from the space where the temperature is lower than the atmosphere. And in the case of a refrigerator, if you take up, then you see this is slightly, this temperature is slightly above that or greater than the equivalent to atmospheric temperature. It is above that. And here, the refrigerator, the cooled space, that means the amount of heat is to be extracted. The important thing is amount of heat to be extracted from this. This is the refrigeration. Therefore, refrigeration, the refrigerator extracts the heat from the cooled space and is being supplied to a temperature higher than the atmospheric temperature. So this diagram you should remember always at what temperatures either a heat engine or a heat pump or a refrigerator works. With this background, this will be easier because if you remember this figure, this is the heat engine and at this end it is the refrigerator. In between it is the heat. Okay. Now with this background, let us try to have the relationships between the performances of these things. How to get? Now let us see. Okay. Now let us start with the efficiency of a heat engine because we are all very much familiar with the heat engine. Therefore, we know this efficiency of a heat engine. What is this efficiency of a heat engine? It is nothing but work done by the cycle by heat supplied to it. Heat supplied to it. Isn't it? Then what is this? This is equal to 1 minus QC by QH. How you got this? How you got this? W cycle. Then what is this? How do you get this equation? Then if you remember this, just now I explained that this is W cycle is equal to, what is this? This is W, this is QH. This is QC. QH minus QC. Therefore, here this is QH minus QC. I have to substitute W per cycle is equal to QH minus QC. If I substitute that, QH minus QC by QH. Therefore, QH by QH comes to 1 and this is minus QC by QH. QC by QH. Therefore, if you see this, what is the amount of heat? It is the amount of heat taken from the hot body. This is always greater than the amount of heat rejected. Therefore, always this is a fraction. This is a fraction. And 1 minus some fraction will be always less than 1. We know, all of us know, the efficiency will be always less than 1. Why? Definitely with this equation, you can easily explain why the efficiency of a heat engine is less than 1. Because this is equal to, this is a QH minus QC by QH. Okay? What is QH? It is the heat taken away from the hot source, and then QC is the heat rejected to cold temperature, lower temperature, or cold or hot body. Hot body and then cold body. You remember like this. This will be very simple. Okay? Heat taken from the hot body and heat rejected to a cold. This is how you can remember that. QH minus QC by QH. This is equal to 1 minus QC by QH. This is a fraction. Therefore, efficiency of a heat engine will definitely be less than 1. Okay? But one more thing. All of us know in the thermodynamics, heat transfer and other things we know, as in it follows that the Carnot theorem process. This is QC by QH. QC by QH is always a function of temperatures of the cold body and the hot body. And we know that this QC by QH is equal to TC by TH. That we know from the thermodynamics point of view, already we have known. But if you take up the textbooks, they will not go to this extent of converting this into temperatures and writing this equation, the solving the problems. If you take up any refrigeration or the air conditioning textbooks, they will not take up this sort of analysis. This sort of analysis is very much required for us. I have taken up here because this sort of analysis is very much helpful to us in order to solve the problems. The very difficult problems are there, especially in the gate you might have gone through very difficult critical problems. Unless you know the analogy, these equations, then you cannot solve these problems. Therefore, this is a QC by QH is equal to TC by TH when the temperature that we choose is in Kelvin. Temperature we choose is in Kelvin. This is a very much important thing to be remembered. Most of the times, students will be going wrong because the temperature usually will be mentioning in terms of degree centigrade. The days of Fahrenheit has gone, and we are in the generation where we are making use of the temperature in terms of its centigrade. In all the problems, the temperature in terms of centigrade will be given to you. If you substitute these values, the temperature Tc by Th in centigrade, then you will come to know that this is not equal to Qc by Qh. Therefore, making use of this knowledge of thermodynamics, this is Qc by Qh is equal to Tc by Th. Now, I would like to replace this equation with the help of temperatures. How? This is the Carnot efficiency of a heat engine. This is equal to, or heat engine efficiency, this is equal to 1 minus Qc by Qh. That's what I have written here. Carnot efficiency of heat engine, this is equal to 1 minus Qc by Qh. 1 minus Qc by Qh. Just now I told you this Qc by Qh is equal to Tc by Th. Therefore, this is 1 minus Tc by Th. Tc by Th. This is further is equal to Th minus Tc by Th. And I told you here, this is a QH minus QC, QH minus QC by QH. Just similar to this here, this is TH minus TC by TH. You have been making use of it. And sometimes this sort of expression. What is this? Cold temperature. Temperature of the cold body, this is the temperature of the hot body. Cold body, hot body. Therefore, this is important equation. Further, this will be very much useful to us. Now, based on this efficiency of a heat engine, how we have written? This is output by input. Similar analogy for performance. Then performance, if you take up a refrigerator, performance, it is defined in terms of the coefficient of performance. Because the standard cycle is the Carnot cycle, it is a theoretical cycle, it is an ideal cycle. The maximum efficiency and the maximum performance you are able to get in the case of a Carnot cycle. Therefore, this is a theoretical one. I am calling this as a Carnot COP. Carnot COP, coefficient of performance of a Carnot refrigerator. Carnot refrigerator. Carnot, here it is a Carnot heat engine. Carnot heat engine, this was on the Carnot cycle, this was on the reversed Carnot cycle. Therefore, this is COP of the Carnot refrigerator. Therefore, for the refrigerator, what is the output? Output is heat extracted from the refrigerator. That's a cold body. Heat extracted from a cold body. That's what it is. Output. I have written this output as Q by C here. Output that I want is QC by the input that you are giving it to you. Always in all the things, the input, it may be a heat engine, or it may be a refrigerator, or it may be a heat pump. The input given, here it is the work. This is here, the work will be there. The work will be there, isn't it? Here it is the output, here this is the input. Work done will be there. In the case of an engine, this is the output. In the case of a refrigerator and a heat pump, this is the input given to it. Therefore, let me define once again what is the COP, coefficient of performance of a refrigerator based on the reversed Carnot cycle. That's what it means. This is equal to output by input, heat extracted from a refrigerator by work done here in the refrigerator. Therefore, this is equal to what? This is equal to work done. This is the heat extracted, the same. What is the work done per cycle? In the refrigerator, once again, in the last slide, if you remember, then if you see here, this is in the case of a refrigerator, what is the work done per cycle? This is taken from this, work is combined is being rejected here. Therefore, this minus this is equal to, this is QH minus QC is equal to work done. Isn't it? QH minus QC is equal to, this is equal to the work done per cycle. This is QH minus QC. Heat extracted, heat supplied. Here, it's applied to this one, and this being combined, these two put together is being given to this. Therefore, this is equal to this minus this. Therefore, it is QH minus QC. Therefore, work done per cycle is equal to QH minus QC. This is QC by QH minus QC. And I told you these are directly proportional. Therefore, instead of this, I can write this as TC by TH minus TC. In terms of temperatures, I can write this as TC by TH minus TC. Okay. Now, if you take the heat pump, this is a refrigerator, we have taken up the heat pump. What is the difference between a refrigerator and a heat pump? It is both of them are same. Only thing is, what is the output that required? Output required in the case of a refrigerator is heat extracted, and the output that we require in the case of a heat pump is heat supplied to a hot body. Okay, this is the output that we require. And what is the input given to this? It is nothing but the work done per cycle. Therefore, this is QH by work done per cycle. Once again, this is QH minus QC. Therefore, this is equal to TH. QH means it is directly proportional to the temperatures I told you earlier. This is equal to TH by TH minus TC. Okay? This is equal to TH by TH minus TC. Then you just try to remember what is this? What is this? Heat. This is the heat engine, and this is the heat pump. Heat engine is the heat pump. And if you compare these two things, how do you compare these two? This is nothing but TH minus TC by TH. This is TH by TH minus TC. Can you identify the relationship between that and this? It is nothing but the reciprocal of this. Very simple. It is TH minus TC by TH. It is TH by TC minus TH minus TC. Therefore, it is the reciprocal of the efficiency of a heat engine. COP of heat pump, Carnot heat pump, COP of Carnot heat pump is the reciprocal of the efficiency of a Carnot heat engine. This is what the statement that I would like to make. You should remember this very well. Throughout this chapter, you have to remember. What is this that you have to remember? The COP of heat pump is equal to 1 by efficiency of a heat engine. This always you should remember. Therefore, this is equal to, this is reciprocal of it, or in other terms, the heat pump if you take up, this is equal to QH by this is what we have written, QH minus QC. This can be written in a different format. Different format if you want to write QH minus QC. This is I can write this as 1 plus QC by 2H minus QC. Can I write this or not? Whether this is equal to this or not. If you see this, take the LCM of these two, QH minus QC. Therefore, QH minus QC plus QC, QC gets cancelled, nothing but QH by QH minus QC. Therefore, I can write this as 1 plus QC by QH minus QC. Why all this exercise? What is my interest? Why should I go for this equation and all? Then you see this and try to identify what is this. What is this? Can you identify this? QC by QH minus QC. QC is the amount of heat extracted in the case of a refrigerator. Output of it, given input is it. This is the COP of a refrigerator. It is the COP of a refrigerator. So what is my effort? My effort is only to relate the COP of a heat pump to a COP of a refrigerator. Therefore, what is this? COP of a heat pump is equal to 1 plus COP of a refrigerator. Therefore, if the same equipment is being used both as a heat pump as well as a refrigerator, then if you know either the COP of a heat pump or the COP of a refrigerator, then your job of finding the COP of other thing is very simple. Therefore, either it is 1 plus or minus 1. It's very easily you can find out COP of refrigerator if the COP of pump is given to you, and vice versa. And vice versa. These equations looks to be very simple, but in some of the times while solving the problems, unless you remember this interrelationships between the efficiency of a heat engine and the performance of a heat pump, and the COP of a heat pump and the COP of the refrigerator, and this not being explicitly given in most of the refrigeration textbooks, but if you take up the problems, especially the gate problems and all, most of them they are with this background, because one relation they want to relate one to the other. If you go to any interview, actually in order to know the knowledge in the refrigeration and all, most frequently asked question is, all of us know the heat engines and all. Then usually, definitely you will come out to say an answer. It is something around some 30%. Usually heat engines, the efficiency is only going to be 30%. That's a maximum efficiency. If the maximum efficiency of this is 30%, then what is going to be the COP? That's nothing but the efficiency of a refrigerator or a heat pump. This is the same question. I have written it here. What is the question here? If the thermal efficiency of a heat engine is 30%, and if it is reversed, this is important thing, and if it is reversed in the operation, if it is reversed, then only it works as a refrigerator or a heat pump, isn't it? To work as a refrigerator or a heat pump with same operating conditions, then what will be the COP, the maximum COP of a refrigerator or a heat pump? This is very important, and most often being asked in the most competitive examinations. Even the gate also it is being asked, where it looks to be simple, and sometimes you get confused. There's no other data is being given. Only the efficiency of a heat engine is being given. And then how do you comment anything about the COP of a refrigerator or a heat pump? Sometimes it looks to be meaningless unless you are very much thorough and very much conversant with the equations and the interrelationship between the efficiency of a heat engine, COP of a heat pump, and the COP of a refrigerator. This idea will not strike your mind. Therefore, with the background. That's why purposefully I have taken up that, and I wanted to tell you the solution for this. So what is the data given to you? It is the efficiency of a heat engine that is being given to you. Efficiency of a heat engine is nothing but the 30%. It is given to you. Efficiency of a heat engine. We know the efficiency of a heat engine is equal to QH minus QC by QH. It is the heat taken from the hot body, is the heat rejected to the cold body by heat taken from the hot body. And this is also equal to 1 minus, this is 1 minus QC by QH. Okay, and this is given as the efficiency is given as 30%, that is 0.3. This 0.3, then this is equal to 1 minus QC by QH. Therefore, what is QC by QH? This is equal to 0.7. Okay? Therefore, now how do this QC by QH is equal to 0.7? This is good, very good. Then how to get the COP of a refrigerator or COP of a heat pump? How do you get that? Then come back to the definition of COP of a refrigerator. What is the definition of this COP of a refrigerator? This is equal to QC, it is the amount of the heat extracted by the heat supplied, heat extracted. This is QC by QH minus QC. We know that. We know that. But the data known to you is only QC by QH. Then I want to get this QC by QH minus QC. Then it looks to be somewhat tricky. Then I know QC, this, then how to get this is QC, this QH minus QC. Therefore, either we can divide this numerator and denominator by QH, or QC is equal to 0.7 times this QH. We substitute that, then this is QC by, this is Q, divide this numerator and denominator by H, QC by QH by 1 minus QC by QH. Okay? This is equal to QC by QH is equal to 0.7 and 1 minus 0.7. Therefore, this is 2.33. 2.33. Therefore, the cycle is reversed, and the same thing in the same temperatures. If a heat engine is being operated as a refrigerator, then the COP of this refrigerator is going to be 2.33. If the same thing is used as a pump, a heat pump, in such case, what is this COP? Once again, by definition, this is equal to QC. Instead of QC, it is QH. QH by QH minus QC. Once again, this is equal to 1 by, I divided numerator and denominator by QH. This is nothing but QH becomes 1. This QH by QH becomes 1 minus QC by QH. QC by QH. Therefore, I know what is QC by QH. This is equal to 0.7. Therefore, 1 by 1 minus 0.7. This is 1 minus this. Therefore, you are going to get 0.7. This 0.3. 1 by 0.3 is equal to 3.33. 3.33. Therefore, how to sum up this? If a heat engine, the cycle is reversed, and if it operates as a refrigerator, then its COP is 2.33. If it operates as a heat pump, its COP is 3.3. Sometimes you need not go for this equation at all in order to find the COP of a heat pump. Then how do you get? We know COP of a pump is equal to COP of a refrigerator plus 1. It is 2.33 plus 1. This is equal to 3.33. That I have not written here, but you know that COP of a pump is equal to 1 plus COP of refrigerator. Therefore, 1 plus 2.33 is 3.33. It's really a pet question for the competitive examinations, actually, in the case of interviews and other things. Okay? Now, let us go a step further for a cycle, ideal cycle for a refrigerator. What is this ideal cycle? Then how do you extract the heat and all? Before that, let me take a break for some few seconds. Now, reversed Carnot cycle. Reversed Carnot cycle. All the mechanical engineers who have studied thermodynamics and all, the Carnot cycle is a very much familiar cycle for all of us. And it is usual for the heat engines and is the ideal cycle for the heat engine. Why we call this as in the case of even the heat engine, we call this as an ideal cycle. It is a theoretical cycle, ideal cycle, because it is impracticable. It is impracticable. Theoretically speaking, this can be followed, but practically there are many difficulties with the help. Then we cannot make use of it. But always we will be searching the ways in order to come near to the Carnot cycle in the case of a heat engine. Isn't it? Just similar to that, because the cycle in the case of a refrigerator is a reversed one. Therefore, we call this as a reversed Carnot cycle. This is a reversed Carnot cycle. A reversed Carnot cycle. Reversed Carnot cycle is being reversed because the heat engine and refrigerator cycles are being reversed. It functions in the reverse fashion. Even the cycles can be reversed. And let me going further. Let us memorize once again what is a Carnot cycle. What processes it involves. The Carnot cycle, it involves two isentropic processes and two isothermal processes. The cycle is reversed, but the processes are the same. That is, two isentropic processes and two isothermal processes. And before going this process, see, two diagrams are being given to you here. What are these two diagrams? It is nothing but the plot between the pressure and volume, and this is the temperature and entropy. This really both are very important. Probably two may be conversant with these two plots in the thermodynamics. We'll be continuing to make use of these two plots even in the case of a reverse. Let us see this. Then let us start our process at point 1. Let us start our process at point 1. What is happening here? This is isentropic 1 to 2. We are compressing. The air is being taken. The air represents whatever you take up. Then this is any gas. It may be a refrigerant or it may be a gas. It may be an air. It may be taken up and it is compressed. See, it is compressed. How it is being compressed? Isentropically, 1 to 2. What is this isentropy? What is this isentropical? It is nothing but reversible adiabatic process. What is this isentropic process? Reversible adiabatic process. Simply we call this as isentropic process. Adiabatic process is one where there will not be any heat transfer from the environment to the system or from the system to the environment. There is no heat transfer. It is zero. Heat transfer is zero. That's why it's called as adiabatic. Adiabatic. And the process is completely reversible. That's why it is called as reversible adiabatic process. Reversible adiabatic process. And this is an isentropic process. And what happens in this? It is, if you see the PV diagram, it is being represented like this 1, 2. It is isentropic. That means isoentropic. Isentropic is isoentropic. What do you mean by that? Entropy in this process is constant. Entropy in this process is constant. Now you see here is the temperature entropy diagram. This is 1, this is 2. The entropy in this process is constant. Only thing is, as this is being compressed, then the temperature has gone up. The temperature has gone up. It's compressed here, then it is compressed in the isentropic process. As a consequent to it, what is happening here? Clearly see from the figure, the temperature has gone up from 1 to 2. Only this, if you see this figure, then definitely you can say that here, if you see this here, then the temperature pressure has gone up and automatically temperature would have gone up. That's what we infer here and we infer here. Therefore, here you can say the temperature has gone up. Here we can say the pressure has gone up as well as the temperature. Temperature and pressure both have gone up. This is the isentropic process. Therefore, this is, and what happens to the value? When it compresses, when it gets compresses, then the volume reduces, volume of the air reduces from 1 to 2. 1 to 2. So, once again, try to sum up this. What is this 1 to 2? A gas air is being taken into the cylinder. It is being compressed isentropically at constant entropy. So, as a consequence of it, the volume has been reduced, the pressure has gone up, and the temperature has gone up. With these two diagrams, you should be in a position to sum up like this. Sum up like this. Okay? Now, the temperature has gone up T1 to T2. It's T1 to T2. Pressure has gone up T1 to T2. Volume has gone down V1 to V2. Okay? Now, the second thing is, now it is being compressed air and is shown in this diagram. The air from this heat, now compressed, this temperature has gone up. Now heat is to be rejected. How do you reject the heat here? Here the heat is being rejected by having a sink at constant temperature. This process, the heat is rejected at constant temperature. By a sink here at constant temperature, the heat is rejected from the point 2 to 3. As a point 2 to 3, what sort of process this is? Isothermal. Isothermal process is a constant temperature process. Therefore, isothermal process, this is isothermal process. It is like this, isothermal. Temperature is constant, but if you see here, what is happening to the pressure? Because the pressure is increasing from T to 3, 2 to 3. Pressure is increasing from 2 to 3. And what is happening to this? During this expansion process, the entropy is coming down. Entropy has come down from 2 to 3, or you can say 1 to 4, all the same. Therefore, T2 is equal to T1 and T3 is equal to T4, S3 is equal to S4 or S2 is equal to S1. Therefore, the entropy has gone down from S2 to S3. Pressure has gone up from P2 to P3 and volume has further gone down. It is V2 to V3. V2 to V3. Volume has further gone down. That's why it's called as compression. Though it is the heat removal here, it is a compression because pressure is increasing, volume is reducing, and this is all happening at a constant temperature. Therefore, we call this as isothermal compression process. That's why we are calling this as isothermal compression process. This is the heat rejection or the heat removal from it. Heat removal also leads to compression. This is a point to be noted. If the heat removal, then if you take up the heat removal at a constant temperature, then it leads to decrease of the volume, increase of the pressure. It gets compressed. It gets compressed. Heat rejection is a sort of compression process. Compression process. That's why this is also termed as the isothermal compression process. Usually what we want here in the case of a refrigerant cycle, heat is to be removed. Heat is to be removed. That means during the refrigerant cycle, the condenser will be there where the heat is being removed. Heat is being removed here. Then what is the amount of the heat is being removed? If the heat is removed, it's okay, well and good. Then in the thermodynamics, you might have seen, if you draw a TS diagram, the amount of the heat removed from this is removed. This is 2 to 3 process is the heat rejection process. Heat rejection process. Therefore, what is the amount of heat rejected from this? The area under this diagram, this is 2, 3, 3 dash, 2 dash. This is the area. This area under this diagram will give you the amount of the heat removed from it or heat rejected by it. Removed from it or heat rejected by it. Therefore, this is the area. It's nothing, it's something like a rectangle. It is 3 dash, 3, 2, 2 dash. Therefore, this rectangle is representing the amount of the heat rejected in the process 2, 3. In the process 2, 3, the area. That's what is being written here. The area 2, 3, 3 dash, 2 dash. Okay. Now, how do you calculate the area? This into this. What is this and this into this? This is this S1 is equal to S2. This is S2 minus S3. S2 minus S3 or S1 minus S4. All the same. This S2 minus S3. He has written this in terms of S2 minus S3 because here 2 minus 3. S2 minus S3. And into this one. What is this one? Here to here. What is this represents? It represents the T3. And here if you see this isothermal process, T2 is equal to T3. Therefore, he has written T3 and this is T2. This is T3 is equal to T2. And S2 minus S3 is equal to the same he has written here. Okay? Therefore, once again, by making use of our thermodynamics knowledge, then if you want to find what is the amount of the heat that has been taken out from the air, gas or refrigerant in this process 2 to 3, then this is nothing but T2 into S2 minus S3. Very simple thing. Knowing these values, heat can be easily calculated. And one important thing always you should remember, once again, I told you, is the heat rejection process, but this is being taken up at constant temperature. If you remove the heat at constant temperature, then it acts like a compression process. It acts like a compression process. This much of explanation is not being offered in the textbooks, but you should understand this. You should understand this. That's why, as I got the opportunity, I am explaining to you that it's not only the heat rejection process. Mostly we say heat rejection, and it is being written as the compression. Sometimes there is isentropic compression and isothermal compression. Why two compressions and all? Always sometimes it will be confusing. Actually, this is the compression and this is the heat rejection. As a consequence of heat rejection, the compression, further compression is taking place. It is not our interest or our inclination, it's not of our interest to compress it further here, isothermal. It is not our interest. Our interest is only to remove the heat here. If you remove the heat at constant temperature, this isothermal compression is being taken up. This is a very important thing to be noted because explicitly this is not being mentioned in any of these textbooks. That's why I am taking time in order to explain it to you in a lengthier fashion. Okay. Now coming back, this 2, 3 is over. This one isentropic is over, isothermal is over, and this has been compression. And 3 to 4, it is the expansion. It is expansion. What sort of expansion it is? Once again, it is isentropic expansion. Isentropic expansion. How do you say isentropic expansion? It is very easy to understand from the TS diagram. Isoentropic, same temperature, same entropy. 3 to 4 is a straight line. Isoentropic. Once again, let me remind you what is isoentropic. It is reversible adiabatic process. Reversible adiabatic process. In this process, reversible adiabatic, there is no heat transfer from that. But because of this, what is happening? This is the expansion. The pressure is coming down. The pressure is coming down. Consequent to it, the temperature is also coming down. The temperature is also coming down, and all this is happening at a constant entropy. Okay, opposite to this here the temperature has gone up, pressure has gone up, volume has been reduced. Isn't it? Volume has been. Here if you see the opposite to it, the pressure has gone down, temperature has gone down, and volume has been increased. Volume has been increased. This is what we should understand. Okay, there is no heat transfer here. Okay, therefore this is 0. And coming to the last one, it is nothing but the heat absorption or the heat addition, or if you see this book, he has written this as isothermal expansion. This is expansion, no doubt this is the expansion process. Here also is the expansion process. This is also expansion process. Then what is that we are doing here is the heat addition that we are doing. It is a heat addition. And how do you add the heat here? Adding the heat with a constant temperature heat source. That means heat is added at constant temperature. At a constant temperature, the heat is being added. Temperature is constant. Temperature, see, temperature is constant. So it is a heat addition. Just similar to this, opposite to this. Here is a heat rejection. This is a heat addition. This is the heat addition. This is the heat rejection. And therefore, this is the expansion process that we are getting. Expansion from 0.4 to 0.1. Therefore, consequent to it, then the volume has been increased from V4 to V1. Pressure has gone down from P4 to P1. The temperature he has, you see, this is the process 4 to 1. The temperature is constant. Entropy has gone up from this 3 to or 4 to 1. 4 to 1. The entropy has gone up. This is heat being rejected, or in the case of a refrigerator, heat being extracted. Heat being extracted from the refrigerator. And I told you once again, this is the heat removal, heat extraction. Then it is also a, see what is happening here? Expansion process. Expansion process. As this is a compression process, this is a expansion process. Okay? This is a very important thing you have to understand. Therefore, if you have taken out the heat from the system, then what is the amount of heat that is being taken out? That means heat is being added to the air or the refrigerant. How much is extracted from this space? Then if you want to know that, once again, the TS diagram will give you the easy process of finding the heat that is being extracted from the source. This is the 1, 4, 1 is the process in the TS diagram. Then we know the amount of the heat that is being absorbed from the system or taken out from it, absorbed from it. What is the amount of the heat? This is nothing but Q41 process. This is a Q41 process. If you see this, this is equal to area under this diagram. 4, 1, 2 dash, 3 dash. This rectangle will give you the amount of the heat that is being absorbed. That is being absorbed from the system. Okay. Therefore, this is T4. This is the rectangle area. How do you find the rectangle area? This multiplied with what is this? This T1 multiplied with this is S1 minus S4. This multiplied with S1 minus S4, or this is nothing but S2 minus S3. S1 is equal to S2 and S4 is equal to S3. Instead of calling this as S1 minus S4, I call this as S2 minus S3. S2 minus S3. Okay? S2 minus S3. That's what he has written here. Okay? Now, what is the work done per the cycle? We are interested to find what is the work done per cycle. Work done per cycle is nothing but the heat rejected to the hot body by heat absorbed from a cold body. Isn't it? Heat absorbed from a cold body. This is what we wanted to know. Heat rejected, here we have seen heat rejected, and here it is heat absorbed. And this heat rejected minus heat absorbed will give you the amount of the work done. This is equal to, if you take up T2 into S2 minus S3 minus T1 into S2 minus S3, this is equal to S2 minus S3 is common, T2 minus T1 into S2 minus S3. Okay? Why we want this? We want this is an ideal cycle and its performance is going to be the maximum. Always we will be approaching towards that and we will be revising this, we will be approaching towards that. Then what is this COP? This COP is equal to heat absorbed by work done. Heat absorbed by work done. Then what is this heat absorbed is equal to T1 into S2 minus S3 by heat, this one, work done, this is equal to T2 minus T1 into S2 minus S3. Therefore, these two gets cancels. It is T1 by T2 minus 3. T1. T1 by T2 minus T1. Though the reversed Carnot cycle is the most efficient between the fixed temperatures. So, in order to find the COP of this, what is that you require? Only T1 and T2? Yes. We require only T1 and T2. What is T1 temperature of the cold body? What is T2 temperature of the hot body? Simply, if I know the temperatures of cold body and hot body, I can easily find the COP of a refrigerator working on the reversed Carnot cycle. Reversed Carnot cycle. Then, if you look at this equation, is it looking synonymous to some other equation? Definitely you can come out and say, yes, this equation is synonymous to the Q1, it is amount of heat extracted Q1 by Q2 minus Q1, and this is given only in terms of temperatures. That's what I said in the beginning. Instead of Q1 I am writing T1, and this is instead of Q2 I am writing T2, and this is T1 by T2 minus. This is also equal to Q1 by Q2 minus Q1. Okay? This is very simple. Then say if this is the efficiency of it, then we know the relationship between the performance of a refrigerator and the performance of a heat pump. What is the relationship? Heat pump performance is equal to 1 plus performance of a refrigerator. Therefore, this is 1 plus performance of a refrigerator. I am taking up this here. If I sum up, this is nothing but T2 by T2 minus T1. Once again, this equation, if you see, this is quite synonymous to the equation. This is equal to COP of a pump is equal to Q2 by Q2 minus Q1. Isn't it? Therefore, it is just synonymous to it. And we know that relationship between the pump efficiency and the pump COP as well as the heat engine efficiency. It is a reverse of it. Reverse of it. Therefore, COP of the heat engine is equal to, or the heat engine, COP of the heat engine or the efficiency of a heat engine. Efficiency of a heat engine is equal to 1 by COP of a heat pump. I reversed it. It is nothing but T2 minus T1 by T2. This interrelationship, many of the refrigeration textbooks in terms of temperatures, they doesn't give. No textbook will give you these things. But for solving the problems, they are being related to pump, heat engine, and a refrigerator. In some terms or the other, they are being related. In order to make it somewhat complicated, and to test your knowledge given one thing and to find the required thing in the other thing. So they will be posing, unless you know the interrelationship between the performance of a refrigerator, pump, and an engine, then unless you understand these things, then it will be difficult for you to go further for this. Therefore, with this is very important. And what makes you then, now this is, I said, is a theoretical cycle and all. What is the impracticability involved in it? What is the impracticability involved in this? If you see this, then what are the limitations of this Carnot cycle? There's the limitations. Impracticability is in it. What is this impracticability? A compression is being taken up, expansion is taken up. Compression, it is nothing but then this is piston move down. Then if something is moving up or moving down, then definitely there will be some sort of a friction. If the friction is involved into it, then there will be impracticability. Some power will be lost, some heat will be lost, some source pressure will be lost. Therefore, this isentropic process, reversible adiabatic process, really very difficult things, very difficult thing. And we can really approach towards that, but exactly isentropic compression and expansion, they are not possible due to friction. Okay. And coming to this isothermal addition, heat addition and heat rejection. At one temperature, their heat is to be rejected and it is to be absorbed. Actually, for heat to be rejected or to be absorbed, we require some temperature differential is required. Some temperature differential. It is quite possible in some processes where there is a phase change. If there is a phase change, then a little bit possibility is there with a little differential, temperature differential, we can do it. But mostly this is very difficult. Not only that, this isothermal heat addition or the heat rejection, this isothermal process, this requires very slow speeds. Unless you go very slow speed, this isothermal process cannot be taken up. On the other hand, in the same cycle, there is isothermal process as well as there is isentropic process. Isentropic process needs very high speeds and this requires very low speeds. Within a cycle, having high speed and low speed is really very contradictory requirement for one particular engine. For anything, it is very difficult. Part of a cycle, it should be very slow. Part of a cycle, it should be very fast. This is quite unpracticable. Therefore, all these are the limitations which makes the Carnot cycle, maybe a reversal Carnot cycle or a Carnot cycle, makes impracticable. Impracticable. So before going to the air cycle and all, I hope this is the time for us to go for some of the objective type of questions, and some problems which actually I have consolidated some of the material that I have received. Some questions have been gathered from the GATE textbooks and some questions from IES examinations, some university examinations and all. So this I can take up in the next class. And before let me take up this thing. Now, some problems I should take up before going to this. 1 minute. Yes, let me take up some problems and let me take a break. You also can take a break for 1 minute for water. Very simple things. This only the data already you know that. The only thing is some confusing data will be given to you. You are required to memory based questions. It's a very simple thing. First part I am taking up the memory based questions. This is the SI unit. This is 1 ton of refrigeration in terms of kilojoules. All of us know it is 210 kilojoules per unit. Answer is A. In order to confuse you, it is given 21, 420, 840. But in terms of the kilowatts, what is in kilojoules? This is 3.5. That's given. Okay. Now, if you know the definition of this, the second question, 1 ton of refrigeration is equal to the refrigeration effect corresponding to melting of 1000 kg of ice. In what time? What is the time required for it? Is it 1 hour, 1 minute, 24 hours, 12 hours? We know that in 1 day it is required. The answer is 24 hours. Once again, this is a memory based one. Therefore, but the only thing is the other alternatives always will be confusing. Therefore, if you really correctly remember these things, then removes the heat from a low temperature body and delivers it to a high temperature body. Here, this will be slightly confusing. Instead of low temperature, high temperature, and other combinations is being given. The only thing is, if you remember this exactly, this is removing the heat from a low temperature body and delivering it to a high temperature body. Very simple thing. You can say the answer is A. I have given it to you so that you can once again go through these questions. And all this also the memory based one. This is the COP of a heat pump working on a reversed Carnot cycle. All of us know this is the heat COP of a heat pump. Pump requirement is higher temperature, that means it is T2 by T2 minus T1. Always this is T2 minus T1 will be there, but it is T2 by T1 minus T2 minus T1. Because this sort of equations in terms of temperatures, the textbooks are not given. This sort of analysis. In terms of the heat rejected, if you see any of the textbooks, they have written these equations in terms of the heat quantities. And therefore, sometimes those who are conversant with only the textbooks and not with the analysis of these temperatures, probably they may find it difficult also here. And sometimes they feel that it is similar to this Q2 by Q2 minus Q1. Probably they may be in a position to give this answer. But if you know this analysis of the temperature, then definitely you can jump to a conclusion that yes, it is, answer is D. It is T2 by T2 minus T1. And what is the relative coefficient of performance? And we know that this is actual COP by theoretical COP. This is the definition says that. Let me not spend more time on this. And go to this COP of a Carnot. Say, if you see COP of a Carnot refrigerator, in winter will be dash as compared to COP of a summer. Whether it will be the same or it will be a lower or it will be higher. Compared to summer, what happens to the summer? The T2 will go up. Therefore, the COP of this is going to be higher. This just a simple, only thing is if you analyze this, you can immediately say the temperature has gone up. Therefore, the COP is higher. And coming to this, the coefficient of performance of a domestic refrigerator dash as compared to a domestic air conditioner. Air conditioner, the refrigerator and air conditioner, if you take up, definitely you can say that the refrigerator, it is less than that of the domestic air conditioner. When we take up this air conditioner, because the explanation needed, I will offer there. Because probably this question needs to be shifted to the air conditioning chapter, then you will be in a position to better understand what is this. Okay, let us not get worried about this, how it is less and all. Explanation I will give it in the time of discussion in the air conditioning. And coming to the next one, the COP of a refrigerator working on a reversed Carnot cycle. Reversed Carnot cycle, then where temperature is the lowest temperature is T1, T2 is the highest temperature, then what is the refrigerator COP? Every one of us knows the T1 by T2 minus T1, the memory based one. Now come to this, a small problem. If a heat pump cycle operates between 27 degrees centigrade and evaporator temperature minus 23 degrees centigrade, then the Carnot COP will be, the Carnot COP, what is going to be Carnot COP? For a pump, usually, we are not familiar with this equation, they go for Q2 by Q2 minus Q1, and how to solve with the help of temperatures, people will be struggling. Therefore, as we know this equation, Now it is very easy for us just substituting the values. But once again, if you substitute this in terms of degree centigrade, definitely you will go wrong. Definitely you will go wrong. What is this temperature? These temperatures are in Kelvin. Therefore, this is 27 degrees. So 273 plus 27, it comes to 300. 273 minus 23, it is 250. Therefore, 300 by 300 minus 250, we are going to get 6 as answer. Is the D. There are two ways you can go wrong. If you write this in terms of only the degree centigrade, this will be wrong. And if you put in efforts by writing the equation in terms of Q, then it will be difficult to solve. Therefore, with this, knowing this equation and knowing pretty well and remembering that this is to be substituted in terms of Kelvin, your thing solution is very simple. Very simple. Okay. Now let us go to the next problem. A heat pump working on a reversed Carnot cycle has a COP of 5. COP is given, and it works as a refrigerator. Taking the work input is given. It is working as a COP of refrigerator is 5, and he has given the work input as 1 kilowatt. What is the refrigerating effect? And once again, come back to the definition. The refrigerating effect by work input it is for the COP of a heat pump. Heat pump is it? No. What is this? COP of a pump he has given. COP of a pump is equal to heat rejected. Heat rejected to the work, isn't it? Heat rejected to this. This Q2 by W, he has given this as 5. Q2 by W, heat rejected, the high temperature is 5. Therefore, Q2 is equal to 5 W. W has given this as 1 kilowatt. Therefore, this is equal to 5 kilowatt. Now, what is that you require? Refrigerating effect. What is this refrigerating effect? Q1. Q1 is the refrigerating effect. What is Q2? It is the heat supplied to the higher temperature body. Q1 is heat extracted from a colder temperature body. Therefore, based on this, once you find this Q2, then you have to find Q1. This Q1 is equal to, we know that this Q2 minus W. Q2 we know, I calculated this is 5 kilowatt, and W just now we have calculated this as 1 kilowatt. Therefore, this Q is equal to, Q1 is equal to 4 kilowatt. Therefore, what is Q1? Heat extracted from the cold temperature body. What do you call this? This called as refrigerating effect. Therefore, the refrigerating effect, the terminology completely, sometimes it will be different. And only thing is, if you understand the subject well, then a heat pump and a refrigerator, both of them are being clubbed together in one single problem. One single problem, and a question is being asked. Therefore, the heat pump and the refrigerator combined, therefore, refrigerating effect is to be determined. Therefore, 2 steps are required. 4 kilowatt, this D is the answer. Therefore, you have to remember these things. Just similar to that, then how to relate heat pump as well as the refrigerator. And some data will be missing. In majority of the problems, they will be combining heat engine, heat pump, a refrigerator, and some data will be missing into it. And with your proper knowledge of these 3 things, definitely you will be in a position to find out the unknown things. And coming to the next problem, the refrigeration cycle. This is operating between the condenser temperature. He has given the condenser temperature and evaporator. The Carnot, this is very simple and straight. Finding the, not like this, is very simple, this thing. COP of a refrigeration cycle, this is equal to T1 by T2 minus T1. Just the only thing is, you have to substitute these values in Kelvin. Therefore, knowing these two, then it's very simple for you to calculate. But even here, sometimes students will go wrong by substituting these values in terms of degrees centigrade. Therefore, once again, I remind you to be careful while substituting these values, whether they are in degrees centigrade or in degrees Kelvin. Coming to this, which of the following is not, this is on the refrigerants, we have not covered in theory this syllabus. So when we cover this, we'll take up that. And refrigerating cycle. air cycles, air refrigeration, reverse Bayernot cycle. In the next class, we will take up this. And usually, in a domestic refrigerator, if you see this, then that or the type of compressor it is used, then it is a piston type of reciprocating compressors are being used, and this will take up in the next class, conventional refrigerants. This is coming to the COP of a refrigerating system. If the work input given to you is 80 kilojoules per kg, work input given to you is 80 kilojoules per kg, and the refrigerating effect is 160, then both are given to you. Definition, not the temperatures and these things. He has given straight away what is the refrigerating effect. He has given the work input. Therefore, simply substituting the definition of COP. This is heat extracted, heat refrigerating effect by work done. This is equal to 160 by 80. 2 you are going to. And coming to this, deriving the, actually sometimes it is given, how do you prove that the COP of a pump is greater than 1, or derive the relationship between a COP of a heat pump and the COP of a refrigerator. Therefore, we had discussed earlier also the same thing. Only thing is, for a heat pump, what is the equation you take up? This Q2 by Q2 minus Q1. And here in the same thing, I have subtracted Q1, added Q1 for the same thing. Same equation, subtracted Q1, added Q1. Therefore, in nutshell, this is nothing but this Q2 minus Q1 by, this is, if you take this, 1 plus, if you take this, then 1 plus Q2 minus Q1 by Q2 minus Q1. What is this? It is 1, gets cancels. Gets cancels 1 plus this Q1 by Q2 minus Q1. Okay? Q1 by Q2 minus Q1. What is Q1 by Q2 minus Q1? Is once again COP of the refrigerator. Therefore, this is equal to 1 plus COP of the refrigerator. Very easy to prove. It's not a difficult thing. Okay? Coming to this, different problems I told you, in different ways they are being asked. A reverse Carnot cycle is being used, and once again the temperatures he has given T2 and T1, and the COP of the cycle, refrigerant cycle, and say the temperature limits of the cycle is 300 Kelvin and 270 Kelvin. Determine the refrigerating effect and COP of the unit. Here a little bit differently has asked this question. Has given T1 and T2, and how do you find the COP? You will be finding knowing T1 and T2, easily you can find out the COP of it. But once you know the COP of it, then how to find the other things? This is difficult. It is, we know COP is equal to Q by W, and what is this? What is this Q and what is this W? This you have to find. Then how to find this? If you see this, for one unit, a reverse cycle working with the compression ratio of this cycles, determine the refrigerating effect and COP of the unit. Say for these things, refrigerating 1 ton of refrigeration if you take up, then 1 if you take up, then COP this becomes, this is equal to 9 times the W, and say if you say Q is equal to 9 into work done by it, then how do you find the work done for it? One more data given to you is the compression ratio is given to you. Compression ratio is given to you as 12. Therefore, compression ratio, this Q is equal to 9 into W. What is W? Given compression ratio from the knowledge of thermodynamics, then we can say that this is equal to 1 by R to the power of gamma minus 1 by gamma. This is a slightly difficult question. You have to remember the knowledge of the thermodynamics and the processes, this reversible adiabatic process, in that what is the work done equation, and equating it to the COP of this, and you have to find the work done for this individually and multiply this with this COP, you are going to get Q. And converting this Q into divided by the 3.5, this 4.42 kilowatts you are going to get, and this divided with 3.5. What is 3.5? 3.5 kilowatt is equal to 1 ton of refrigeration. That is not being shown here. This is equal to divided by 3.5. it comes to 1.26. Slightly complicated problem unless you have this exposure, unless this point strikes to you that given the compression ratio, how to calculate in the reverse Carnot cycle, this entropy, isoentropy process is being used, the reversible adiabatic process. In that process, what is the equation for the work done? If you remember that, then if you substitute that in this here, and if you can find the COP of it, if you relate these two things, then only you will be in a position to get this, and you have to convert this once again in terms of tons of refrigeration. Probably you might have given the answer in tons of refrigeration. Therefore, slightly complicated one. And coming to this, how do you produce, how do you find the amount of the ice produced? Once again, in the knowledge of the COP, amount of the heat extracted, this type of problems can be solved. It looks to be lengthy problem and all, and even for 2 marks, this question can be easily asked. Not that difficult. Even the gate, it can be asked for a 2 marks question. This say water temperature is given to you, and the tonnage of a unit 150 tons it is being taken up, and operating temperatures are -5 degrees centigrade, and this is 28 degrees centigrade operating. Evaporator is -5, this is a condenser is 28 degrees, and the latent heat of ice, instead of 335, he has given this as 330 kilojoules per kg. And if it is not given to you also, then because this is a standard value, you know, then you have to substitute this value. You have to determine the mass of the ice produced per day, as well as you have to find out the power that is required to you in terms of this. Okay? Now, what is this? Now, let us take up once again. It is a degree centigrade. You have to convert this in terms of the Kelvin. In terms of the Kelvin, it is to be converted. T1 is equal to -5. -5 plus 273. This is equal to 268. Similarly, you convert this into Kelvin. You'll be getting it. Knowing the temperatures T1 and T2, it's a really cakewalk for us to find the COP of this refrigerating unit. This T1 by T2 minus T1, this is equal to 8.12. It is easily you can calculate, isn't it? 8.12. Then, what is the refrigerating effect? Q. Because you have to calculate how much amount of heat is to be extracted. How do you find that? Because you need to get 150 tons of refrigerant. So, in order 1 ton of ice, therefore 1 ton you require tons of refrigeration here required. This we have to relate. Tonnage of the unit 150 tons, 150 tons of ice, 150 tons of refrigeration. This sometimes it will be confusing. 1 ton of ice requires 1 ton of refrigeration. Once again, this point you have to remember. Sometimes you may be knowing that as a part of definition, but while analyzing this, understanding this, and implementing this in the problem, sometimes it will be difficult. Therefore, this Q is equal to 150 tons of refrigeration. This is equal to, how you get this? 1 ton of refrigeration is equal to 3.5 kilowatts. Therefore, 150 into 3.5, you are going to get is 525 kilowatts. You know Q, you know COP, then what is W? Work input can be easily calculated. Therefore, COP is equal to 8.12 as we have determined here. This is equal to this Q by W. This Q we know and W we doesn't. Therefore, we wanted to know what is the power required for this. Return this. Determine the power required for it. Okay? Power required. Therefore, this is equal to power required for this is equal to this 525. This 525 divided by W. This we are going to get this as 64.65 kilowatt. Actually, K should be small, W should be a bigger letter. Kilo For Kelvin, we'll be making use of capital K, and for watt, we'll be making use of capital W. Therefore, if we simplify this, we'll be getting 64. Therefore, actually, if it is from 0 degree centigrade to 0 degrees ice, 1 ton of refrigeration, but here heat is removed from the water, not from the 0 degree centigrade, but the heat is removed from 22 degrees centigrade. The water is not at 0 degrees centigrade. Water is at 22 degrees centigrade to form the ice. Therefore, what is the total heat required that you should calculate? What is the total heat required? Therefore, latent heat, you should know the latent heat is equal to how much and what is the sensible heat. Sensible heat, how do you calculate? Sensible heat, we know the temperature difference, delta T is there, and is the Cp at constant pressure, specific heat at constant pressure, and the mass of it. Therefore, per kg first you have to calculate. Per kg, if you calculate how much is the latent heat, you know, he has given it as 330. 330 latent heat per kg, we know, therefore 330 plus mass, we are assuming this as 1 kg, therefore per kg we will be finding it. 1 kg multiplied with Cp, we know 4.18, and this is delta T. Delta T is 22 minus 0, and altogether this is 421.96. It is per kg, kilojoules per kg. This is the total heat to be removed from water at 22 degrees centigrade. Therefore, what is the mass of the ice produced? Then if you want to know, then is equal to mass if you want to know total heat required by refrigerating it. If you see heat extracted, then if you calculate this, this is, if you calculate that, then you will be in a position to get this. This if you see, per kg, this is 525. What is this 525? If you see, this 525 is the refrigerating effect, isn't it? For this 525, you require this much amount of this is equal to, this much is to be extracted. This is a refrigerating effect is required. But per kg, how much you are going to get? This is the amount of the heat required to be extracted. Too many kgs are to be extracted. Therefore, from this, if you divide this, is a 525 kilowatt, that we will be coming to know this is equal to 1.24 kgs per second mass you are going to get here. Therefore, mass of the ice in terms of second, we know this is produced in terms of kgs per second. And if you want to know, he has asked what is the mass of the ice produced in 1 day. Daily this 24 into 60 into 60 into 1.24. It comes to so much, 1,07,498 kgs. And some of the other questions, if you see, the coefficient of performance of a refrigerator working as a heat pump, what it is. Even the gate also it is being asked several times. A relationship I told you, it is being asked very frequently, then you should know. All of us know, once again, let me repeat this, heat pump is equal to the refrigerator plus 1. This explanation is also being offered here, less than 1. If some same refrigerator starts working as the heat pump, then COP heat pump is equal to COP. We know that, we are repeating this. And industrial heat pump operates between the temperatures 27 degrees and minus 13 degrees. Then the rates of heat addition and heat rejection are 750 watt and 1000 watt respectively. The COP of the heat pump. What is the COP of the heat pump? Then we have to find COP of the heat pump is equal to how much? Q1 by Q1 minus Q2. Equations values are given to you. Therefore, the job of finding, simplifying this is very simple. This is overworking. And the irreversible heat engine extracts the heat from high temperature source at a rate of 100 kilowatt and rejects the heat to a sink at 50 kilowatt. The entire work output of the heat engine is used to drive the reversible heat engine pump. Reversible heat engine pump, it is used to drive the reversible heat engine pump, operating between a set of the independent isothermal heat reservoirs. Isothermal reservoirs are 17 degrees centigrade and 75 degrees centigrade. The rate at which the heat pump delivers the heat to high temperature sink is. Then if you calculate that, then actually the simplification has not been shown. You take this as a homework and then see is a very simple thing relating between the heat engine and a heat pump. Heat engine and heat pump. The answer you should get to this is C. This is 300. Simplification is not shown here. It takes more time for me to write here. Therefore, and it's not a big thing also. It's very simple, and only the relationship between you see heat engine and a heat pump related. Reverse the operations of it. First get the temperatures in terms and then the heat. Therefore, you will be getting this answer. It's not a difficult thing. Coming to the next one, a Carnot cycle refrigerator operates between this 250K and 300. Its coefficient is direct question. Direct question values are given to you. You substitute, you will be in a question to get this. And round the clock cooling of an apartment, it is having a load of 300 megajoules per day. In an apartment, a load is there 300 megajoules per day for an air conditioning plant. It is to be removed. Then, what is the capacity? What is the capacity? Then it's very easy to calculate. It is 300 megajoules, isn't it? Megajoules per day. Then, what is this mega in terms of kilojoules? If you take up kilojoules per minute, megajoules means 300 into 1000 kilojoules divided by the 24 per day, 24 into 60 into 210. Simply you are getting 110. Problem looks to be complicated, but this is very simple. Very simple. Just simplifying this, you will be getting this. And many problems are there like this relating the heat pumps. A heat pump works on a reversed Carnot cycle. The temperature in the condenser is 27 degrees and in the evaporator coil it is 23 degrees. The work input is 1 kilowatt. Therefore, what is how much heat is pumped? How much is the heat pumped? Heat pump, then therefore COP equation if you take up, what is the COP is equal to Q1 by W. This is equal to T1 by T1 minus W. With this, you'll be getting the Q1. Once you get a Q1, this Q1 is equal to this W into this COP. Therefore, W is equal to 6. Simplification of it. Not very difficult. You can easily see this. And the heat pump is used to heat a house in the winter and then reversed to cool the house in the summer. Cycle is being reversed. The inside temperature of the house is to be maintained at 20 degrees. The heat transfer through the house walls is 7.9 kilojoules. And what is the minimum power required to drive the heat pump? Once again, the definition of the heat pump that take up. Heat pump is nothing but the amount of the heat they projected to it by work done. This is T1 by T1 minus T2. This, if you calculate that, you'll be getting this. And this is equal to, therefore, W is equal to 1. These questions are being asked in the Indian Engineering Services. I collected from some books. Therefore, these things, this is very easy. A refrigerator based on the reverse Carnot cycle works between two such temperatures that the ratio between the low and high temperatures is 0.8. If the heat pump is operated between the same temperature range, instead of that a refrigerator, a heat pump is operated in the same temperature range, then what would be its CO? Reverse it. Therefore, this is the T2 by T1 is equal to 0.8. If the reverse is, this is given as a 0.8 because if it is low temperature, range is given as 0.8. You take this and COP of the heat pump is equal to T1 by T1 minus T2. Therefore, if you substitute this value, then you are going to get a simplification and you can find that this is a refrigerator working on a reverse Carnot cycle as a COP of this. It works as a heat pump and consumes this. Very simple thing. This equation, heat pump is equal to refrigerator plus 1. Like this. So many of the things very simple, and equations between that and this being asked, and you can I feel the time is coming to an end. Therefore, 1 or 2 minutes is there. but many more problems are there. Probably I may be in a position to take up this in the next class, and because many more are remaining. Even the theory, the air cycle I will be taking up, and other things. How to simplify. Other things, the remaining problems also we can see. Simplify. The time is over. Now I am concluding my session here. Concluding my session here. Escape with it.